So I realized I may have made, I did make a mistake right here. That y to the first, I was going by my general form of the binomial. That's supposed to be an h. And I don't believe I did that anywhere else. So we're about to say that there's stuff to cancel, and that would be the x to the n and that x to the n. And what you're going to be left with is the rest of these terms over h. Note, however, that every one of them will have at least an h in it. So what we're going to do is divide an h out. So that has an h in it, that has an h in it. So we'll be left with n, choose n minus 1, x to the n minus 1, and the h will be gone. The next term, which I don't have written in here, has two h's in it, h squared. So it actually would be n, choose n minus 2, x to the n minus 2. It was h squared divided by h is now h. And then we go forward from here. This term has h to the n minus 1, so we'll subtract, that's a 1. Subtract one of those h's away, it'll be n minus 2. And then this will be h to the n minus 1. But important to note here that we're taking the limit as h goes to 0. That term will go to 0. That term will go to 0. That term will go to 0. All these terms, in fact, will go to 0, except for n, choose n minus 1, x to the n minus 1. Now, n choose n minus 1, that's n factorial over n minus 1 factorial 1 factorial, and that's equal to just n. Sorry, I didn't write my x to the n. And then this whole expression is equal to n, x to the n minus 1. So that's going to be the derivative of x to the n. So if we want to take the derivative of something raised to the nth power, we multiply the entire, the term by n, and then we raise it to the one less power. So for example, for g of x is equal to x to the 100, g prime of x would be 100 x to the 99th. For h of x equal to, let's say, 5x squared, h prime of x is equal to 10x. Notice we took the 2 and multiplied it by the scalar multiple. Didn't prove that already, but it's a pretty easy thing to prove. So any of these would work, and then of course, I don't know, k of x. If k of x was x to the 2/3 power, k prime of x would equal 2/3 x to the, now we have to drop this power down by 1, so it'll become negative 1/3, which could be better written as 2/3 cube root x. So these are just 3 examples of applying that principle. Now we'll extend it to polynomial functions. So I'm going to remove this proof. And it's a pretty easy extension, but it basically says if you're adding a bunch of those things up, then you can just take the derivative of each of them individually and add them. For example, if we have a function that is 5x plus 3x to the 5th plus 9 minus 2x to the 7th, then we can do each of these terms individually. So the derivative of 5x, think of this as 5x to the first, will be 1 times 5, that's 5, x to the 0 being 1. So we get 5 for that one. This will be 15x to the 4th. Derivative of 9 is 0. It's a constant, we already proved that. And then subtract away 14, 7 times 2 is 14x to the 6th. Just a couple things to note here. One is this was a linear term, 5x. and we know its slope is 5, so of course its derivative will be 5. The fifth term went to the fourth. The constant term we've already proven went away. So we've now done derivative of constants, derivative of anything to the n, and then derivative of polynomial functions involving those two things interacting. We can just treat them all individually. Okay.